Hey there everybody. In this video, let us look at an experimental Atwood's machine. So I've got up on the board a diagram of a vertical Atwood's machine, and then I've used a smart card to create one in my lab. So that smart card is connected by a string, which goes way up over that pulley there, and then the other end of that string is connected to a hanging mass. And just like in the diagram there, the ratio of those two masses is 5:4. 5M being the cart with a mass of 250 grams, 4M being that hanger with a mass of 200 grams, for M being 50 grams. So what I've got is this thing connected to the capstone program. And because the cart's going to be falling instead of rolling along something, the wheels, which would normally give me the data, aren't going to be turning. So what I'm going to rely on instead is the internal accelerometer. And so I've got acceleration graph pulled up here. It's not going to give me as nice of data as the wheels do, but we should be able to still get what we want from this thing. And so I can get the acceleration of this thing as it falls, and then later on I can also get the tension in that string. So let's set this right here, and kind of wobbly there. That's fixed up. All right, tripod, come on. All right, there we go. So we should be able to see it fall and collect the data at the same time. So when I let this thing fall, I'm going to lift the cart up just a little bit, but not so much that it goes by the mass, because I don't want these things to knock into each other as they fall. And then I'm going to move this little step ladder out of the way. Okay, so we're going to hit record. All right, so right now the acceleration is reading 0. Fall. Okay, beautiful. So let's get my step ladder back in here to hold these things at rest. My string kind of got tangled on the bounce. Please hold. There we go. Okay. Alrighty, so let us go and investigate our data real quick. So you'll notice that the acceleration was originally 0, and it wobbles a little bit, but then we see this real distinct drop off right before 4 seconds, and that's its accelerating downwards moment. And then you see all this, whoa, and that was me catching it. And so as I caught it, it oscillated like a whole lot, and we get all this crazy acceleration here at the end. So we just want to focus on this part right here from about 4 to 5 seconds. And so I'm going to do that trick again where I draw a box. Let's see if I can bring the mouse over here. So there's my box. I'm going to shrink it down. I just want this part where it's falling. Like that. And then I want the average of that. So let's click on the statistics tool there. And you'll notice I get an average acceleration of 1.2 meters per second squared. I'm not going to worry about the sign because that just the direction of the cart is determined by the accelerator built inside. And so because it was moving down and it thinks positive x's in towards the hook, it gives me a negative value. So all I really care about is the magnitude. So let's go over here and write down an experimental acceleration of 1.2 meters per second square. And then let's see if we can get the tension in the string, doing the same thing. So I go back to capstone. I'm going to switch this to a force versus time graph. And notice that we have tension in the string is relatively constant, and then right before 4 seconds, notice that it goes up a little bit, and it stays pretty constant. And then we get all this crazy bouncing, wow, as I caught it at the end. So again, we just want to select that 4 to 5 second range. So I'm going to draw a box like that. Shrink it down a little bit, not too far. Kind of like right there. And then again, it's already got the statistics tool selected. And so reading the tension, I get an average tension of 2.11 newtons. So again, let's write that over here. 2.11 newtons. Okay, so after we get done working the theoretical physics, we can check to see if our numbers match. Till next time, ta-ta.